start. I'm very pleased to introduce you Dan Thomsen from Tresys Technology. Dan has been working, is very well known in the security area. He has been working on security for more than 17 years. And he kind of was one of the first persons to propose the notion of type enforcement.
My company, I was there.
His company.
I was there.
Yeah, he was there. And actually he has a lot of experience in working on various research topics. And what I really, really knew about his work was more related to tools for specification of access control and security policy. So I'm also glad to say that this year he is the program chair for the AXAC conference, which is Application Security Conference, very well-known conference.
Right, and I have flyers here for that, actually, if you're interested. Right.
So I leave him to his presentation.
All right, so what I'm going to be talking about today is I've been doing analyzing security policies, and that's what I've been doing for the last year. I've been at Tresys off and on, and so I was going to talk about that and some of the engineering choices you have to make when you're analyzing security policies. It's really a whole new area, and it sort of ties into software engineering. Security policy engineering is sort of a new area, and I'm going to talk specifically about what we're doing for type enforcement. So basically, I'll talk a little bit about the security environment where I'm analyzing the policy and trying to improve security. And then I'll go into some of the patterns that we use to improve security, how we modify the policy or modify the software to improve security, some of the tools you have in your bag to sort of improve security. And then I'll talk about the actual analysis. What do we look for when we're looking at a policy, trying to make the policy better? What are we trying to optimize when we make the policy? And then I'll talk specifically about the information flow analysis that we're doing as we watch data move around. Now, to some of you, what the kind of analysis I'm doing, the in-depth analysis, might seem really odd. And so I wanted to give a couple slides on why we're doing this the way we're doing it. Why, as you'll see later on, it basically becomes a big graph problem we're trying to optimize in a very particular way. Why are you trying to optimize the graph that way? It doesn't make sense. There are other factors that you might want to do. Well, it really gets down to a matter of economics. At each stage in the process development for software, we're finding that economics are a huge factor. Well, there's also a similar set of factors that apply to computer security that make it quite difficult. So some of the questions arise, what operating system are you using? That determines what kind of security controls you can put in place. And then it determines how much granularity of control you have and what kind of tricks you can have in your bag for improving the security of the system. How much analysis can you afford? When I was at Secure Computing years ago, I worked on a high assurance platform where we had 10 mathematicians working about proving aspects about the system. Very expensive. So if you have that kind of level, you can do a lot more analysis. Then the bottom line comes down to how much does it cost if you get compromised? So and the bottom line, this last bullet here is the really important point. If you say, I'm going to do ivory tower security, and I'm going to spend all the money I have, and I'm going to build the greatest system, that the most secure system ever, but you never get to release the system because you're spending so much time on it, people will march forward, and they will use whatever existing technology is out there, and they will make do with much less security. So the idea is sort of here, that you'll see me as I go forward, is get the most security out there as fast as you can, and then incrementally improve it. Just to characterize it a bit more, commercial versus government. In a commercial arena, what they'll often do is they'll buy insurance. If I get a compromise or my system fails, that's traditionally how they handle it as insurance. I'll pay some a little bit of money now, and if I get a really catastrophic failure, the insurance company will cover me. They'll also do it with software license agreements, right? If the software breaks, it's not our fault. And then, of course, the other problem is they have a financial goal, right? Their whole job of a company is to make money. And so if they have a compromise, it might cost them X amount of money. So they can look at that and they say, okay, it's going to cost us Y to fix it. If we get compromised, it's going to take X. They balance it out and they make a decision. In the government arena where I'm working and analyzing these policies, those financial equations don't really work because the costs are too high. Maybe you're talking about loss of intelligence data, or troop movements. I mean, so you're talking about loss of human life or loss of, strategic advantage. They're huge. You really can't put financial factors on that. So that gives you a little background of why we're doing all this complex analysis. The target mechanism here we're going for is security enhanced Linux. This is an operating system project that came out of NSA. It's one of the few projects that comes out of NSA that has an open outreach where they're trying to get people to use it. Normally they're very hush-hush about whatever they do. So, but they took Linux, a mainstream operating system. They have security hooks now, and so they put out another layer in the kernel then where they basically have these security operating hooks for doing type enforcement. And it has other security hooks as well, like a multi-level secure policy and other things. But what we're interested in today is a type enforcement, and I'll talk about that in a minute. But the important thing here is it's a mandatory security policy. The kind of traditional access controls you find in a Unix operating system are discretionary, meaning the users set them up, and the system administrator sets them up, and maybe he puts some guidelines on you. But as I'll show later on, there's some problems with those types of policies. So you really need to really improve the security of your system. You need to have a mandatory security policy. As I said, a lot of this gets back to economics. SE Linux is freely available. Now, the analysis you'll see is expensive, that what I'm going to do, but at least you've got a free mechanism, and you've got a chance of getting people to buy in and start using this policy to improve the quality of systems. Now, Linux is not a high assurance platform, and if you look around, there are no high assurance platforms because they're very expensive and hard to build. And I'm talking about the common criteria where they evaluate systems, and they have various levels like EAL1, EAL2, EAL4. Now, Linux itself has been evaluated at EAL2 and 3 for different applications. And there's an EAL4 plus evaluation underway. The higher levels, like 5, 6, and 7, are really quite difficult, and they'll be very difficult to do for an open source system. But the point here is that SE Linux has the right security mechanism. And because of those economic arguments, you have to grab what you got, and you have to move forward, or you're not going to improve the security at all. So what is type enforcement? This is the whole reason we're going with SE Linux. It's because it has this mechanism. If there was another high assurance operating system that had this mechanism, it could be a very viable approach too. It's the mechanism that's really interesting here. So type enforcement is a mandatory policy, which means that the system designer sets a security policy when they build the system. It's not up to the system administrator, and it's not up to the end users. This is a very important point, which I'll get to later. Unlike some other mandatory policies, it's very flexible and is very granular. I can control what kind of signals you can send to another process running in a different domain. So that kind of control gives you a lot of power for enforcing security policies. The other advantage of type enforcement is it fits reality. If you look at the LaPadula model, which is a breakthrough model, and it's your classic military model of an unclassified level and a confidential level and a secret level and a top secret level, and the relationships, if I'm at top secret, what data can I see, what data can't I see? It matches what you'd expect. And there's some breakthroughs in there, like in the star property and what have you, about not having the ability to write data down. If you're a top secret and you can read top secret data, you can't write unclassified information, because a Trojan horse running at a top secret could then take top secret information and, unbeknownst to you, encode it in unclassified information. Now, that was a huge breakthrough. But the problem with this sort of strict hierarchical model is it doesn't fit a lot of real-world cases. Even in military environments, obviously they have this unclassified, secret, top-secret hierarchy, but they have real-world applications where type enforcement fits much better. The granularity and flexibility of type enforcement comes at a cost, though. You have to configure it, and you have to get it right, or you really haven't bought anything. So, when the LaPadula model, you have this nice mathematical statement of the policy. That's great. You know what you're going to do. Maybe it doesn't fit reality, but you know what you've got there. With type enforcement, you have to set it up to make it correct. So in type enforcement, in a nutshell, basically there's a resource. It's a file, a socket, a process, there's a bunch of other things, but it's basically a resource. And so then you have a big matrix, and you basically assign how each resource can access each other resource. So in particular, they're processes. And how can the processes access a file? How can the process access other processes? And so you build up this big matrix, and you explicitly define what each thing can do. So it sounds sort of simple, but again, since the system designer does it, it's much more powerful than having a system administrator do it, because you can actually then analyze it and make sure that the property enforces, excuse me, that the policy enforces some properties. At the bottom here, where you see type shadow and stuff, this is some examples of the SE Linux policy language. And I don't want to get into details of what the actual language looks like. But, you know, basically you declare types. You declare the file type there says it's a kind of an attribute. This in particular deals with the shadow password file. And then the bottom line is a very simple statement, you know, authorizing everybody that has the authorization attribute access to read the shadow password file. So it's a very simple statement there. So type enforcement basically organizes the entire system into domains. And for each domain, there'll be a set of processes, and those processes can do something that's defined by the domain set up by type enforcement. So a process has a tied-in executable that's tightly associated with it, because that determines what you can do in that domain. So the program is a set of instructions for that. Let me give a more visual thing here. So what type enforcement does basically is take your system, say this abstractly represents your system, and divides it into a bunch of mandatory little cells. It's like the watertight compartments on a submarine, right? So if there's a hole, a puncture in the hull, like the water doesn't spread to all the other compartments. Here, say the puncture would be an attacker coming in, and they get into one domain, like say maybe your sendmail server is sitting over here, and now they can get into that domain, but then the cell-like structure of type enforcement prevents it from spreading, from the attacker from spreading to other things, which is a common thing in the early systems. Sendmail would run as root. Once they got control of sendmail, they could take over the whole system. So on a type enforcement system, there is no root. Now, in reality, you know, you've got this nice sort of clean model where you've got all these cells. But of course, just like a submarine, you have to connect all these dots, right? It isn't, you know, if you had a submarine where all watertight compartments and nothing moved between, basically you'd have to go into port to get to the mess hall, right? So what you have to do is you have to carefully, in a real system, is punch holes between all these cells and carefully monitor how you move data between the cells. So like if you had sendmail sitting over here, right? You want the mail to be able to get out of the sendmail domain and go into people's mailboxes. So this is where it becomes sort of a really challenging problem. All right, so let me talk a little bit now about the security engineering with type enforcement. Type enforcement, as I said, is a mandatory policy. And the benefits of a mandatory policy, the main thing, if you look at what they're doing, is a mandatory policy stops a Trojan horse. And I gave a sort of a brief example of that earlier. But that's what you're really trying to prevent here. Because, you know, say a user downloads a program off the internet, they're running it in their environment, and they think it's going to calculate bowling scores or something like that. Well, that program possibly could be doing something else that they don't know. An end user doesn't really know what a program does. So the idea here is with a mandatory policy, we will say we will contain that program so it can only write into that one particular space having to do with bowling scores, say if that was the example. So the idea behind type enforcement is it can constrain and contain code and programs that you don't know a lot about. And that gets you a lot of leverage in stopping all these problems. The other thing that goes on is you can't stop everything, but with type enforcement, you can set up a mandatory least privilege policy. Now, the point of least privilege is you give each program only the permission it needs to do its job and nothing else. That sounds simple, but in reality, a lot of programs, they actually access a lot more resources than they need, or what resources the program needs isn't even well understood. So, but if you think about it, if you have a program like sendmail, there'd be no reason for sendmail to go write the web server. So if you use type enforcement and you take that ability away for the sendmail to write the web server, you've basically shut down a bunch of avenues of attack. And so basically you keep analyzing the system, taking things away that aren't needed, and you've really increased the workload of the attacker trying to break into the system. If you don't have that extra privilege sitting there, you can prevent the system from being abused. You can stop certain classes of abuses. Now, you can't stop everything. But now the bottom line here is this is all great. Everything on this slide is great, but it means that the policy has to be configured correctly. Because if you don't have the policy correct, then maybe sendmail can write to the web server, and then that would be bad. So you have to do an analysis to make sure that that doesn't happen. Now, these next series of slides, I'm going to talk about some of the design patterns when you're engineering a security policy for type enforcement that you have. These are sort of basically the tricks that you have in your bag so that you can apply them to the system and sort of resolve conflicts in ways that actually improve the security of the system. The big thing that type enforcement is good at is these things called assured pipelines. This was done by the original Boebert and Kane paper. Earl Boebert worked at Secure Computing where I worked, and he's the one who came up with type enforcement. And this is one of the prime applications that he came up with, was this idea of a labeler. Now, in the DoD world, right, you got this top secret thing, right? If you want to have a top secret file and you want to send it to the printer, it's very important that when it gets printed out, it says top secret at the top. Otherwise, you could just get past your security problem by printing out a top secret file and saying, oh, it's unclassified, and handing it to somebody, walking it out right out past the security guard or something. So the idea behind the assured pipeline was to set up a series of filters, like A goes into B, that goes into C, and make sure that each stage in this pipeline is executed in order and no stage of the pipeline can be bypassed. So in the example that Boebert used was this labeler example where you have an application, say it's Microsoft Word, right? Now, you have no chances of assuring Microsoft Word, or say it's Emacs, right? Emacs, another large program, is going to produce a text file. Because then you can write a very small labeler program, right, that every 66 lines it inserts the label top secret, right? That's a small program. You've got a really good chance of analyzing that and getting it right, that it labels it correctly. Are you going to analyze Emacs and make sure that Emacs can, of the thousands of lines of code in Emacs, you won't know that some other module in Emacs doesn't mess it up. So here you can make a small program and analyze it, make sure it's right. So what the labeler does is it can read the raw data, and then it can move it into the labeled data section. Now, the printer driver then can only read labeled data. So here's another problem that exists in a lot of Unix systems is you have global permission for everybody on the system can read a file. When you have that, you can't do assured pipelines. Because here, the printer driver then could then say, go read off some file in temp that maybe was improperly labeled and then print that. But with type enforcement, you can constrain the printer driver so that it can only read labeled data. And that's huge for reducing the assurance burden. Because now you don't have to analyze the printer driver code to make sure that it's not going off into the wrong directory. All you have to do is analyze it to make sure that it doesn't mess with the content of the data or remove the labels in some fashion. All right. This is another design pattern. This is probably a much larger design pattern, but I call it buckets. Basically, if you have two buckets of paint, one red and one white, if you want to keep the paints, if you don't want to get pink paint, right, you keep them in two separate buckets and you don't mix the data. On an information security system, what happens invariably is people will say, I've got a computer system, and the computer can keep track of if this molecule is red or if this one is pink, white, and I'll keep them separate in the database. It'll be great. So you basically take the two buckets and you mix it all up. Well, now you have to trust the database or whatever program that's separating the data to make sure it doesn't actually mix the data. So the basic pattern here is if it's important that the data be kept separate, you keep it in two different buckets. And that's a common problem you can apply to lots of different things. And as you see through some of the examples I'll work on later, that basically separation is one of the huge things you try to do to prevent contamination of data as it moves around. The problem is, again, like that system I had with all the cells, right? Though that's a nice picture, but in reality you have to poke lots of holes. So even with simple separation, it doesn't really ever become that simple. There's always something that has to move between, and that's where the interesting analysis comes in. All right. Now, another problem, and this one is sort of difficult to explain, but this is the idea of a subdomain. So if you look on the left there, we have the administrator, right? Say the administrator, he can write those three files. He can read and write those three files. But maybe what you're really concerned about is the data that gets written into file 1 could somehow get leaked into file 3, and that would be bad. Maybe that file gets publicly displayed on a web server or something like that. So that would be bad. But the administrator needs to be able to read and write those files. Okay, that's a problem, right? So you could have this data, a Trojan horse here, or even an unwitting user, which is your more likely case than a Trojan horse, could get this data moved over there, and you've got a problem. So you want to come up with a mandatory security policy that prevents that. Well, what we do on the right then to solve that is create subdomains. So the administrator then sits out there, and then he can execute basically small subprograms like SD1. Now, all SD1 has permission to do is read and write file 1. Okay? So if the program in there tries to write anything into file 3, the mandatory policy stops it. And so if the administrator needs to write file 3, he can. He just has to go out and he has to run SD program SD3. And then he can read and write file 3. So that's another really important pattern that you can use to solve these problems. Now, and then here's the third, I think it's the third and final pattern I have here. And I guess another thing I want to stress, too, is this sort of, not a lot of people use type enforcement. Secure Computing, the company I came from, they use it in their Sidewinder firewall, which is a commercial firewall that had great success with it. But they make a very static type enforcement policy. They don't have to engineer it anymore. They got it set up once, right? They analyze it. It's done. It's not a generic operating system where people are doing new applications to it all the time. I mean, they'll add a new filter and they'll put type enforcement in it to protect it, but it's a very rare event for them. So what's missing here is type enforcement engineering. Secure Computing has some expertise in it, and now that SE Linux is available, that expertise is out there, and it's starting to grow a little bit. We've also seen some people do some very stupid things with type enforcement where they don't understand some of the powerful tools they have in their bag. That's why I'm going through all these patterns. So this third pattern here is wrapping untrustworthy programs. Say, for example, you have a policy where you don't want any words containing project names to go out of your company. Maybe it's the secret code name like Palladium, and you don't want anyone outside to know that. Well, if you want to analyze a POP client to make sure that it doesn't contain, no outgoing mail messages contain the word Palladium, you'd have a very large program to have to analyze it if you want to make sure that it's doing the job correctly. It's a lot of work. But you could write a very small program that looks at the body of the text of the messages or looks at the whole message and makes sure that none of the message contains Palladium. I mean, that could be a 30-line program, say. And so you could actually analyze it. You have hope of doing that. What you can do then using type enforcement is you could have the pop mail client work just like normal. The user uses it, the client application talks to it, and just as before it sends the data out, you make sure that it has to go through this little program you've written, and it does the filtering. And now you've got a high assurance system that's going to make sure that none of your sensitive words go out. Now that's sort of a contrived example, but that sort of shows the pattern of where you can maybe put a small program in front of something and increase the assurance. All right. Now, this is an example of SE Linux policy. This is having to do with the password file. And I really don't want to get into the language of the SE Linux policy language. Unless you're going to use it, it's not that interesting. But I just want to show you some of the things that are here. You have declare types. You then they make heavy use of macros. That temp domain password is actually a macro that expands into the ability to write to temp directories. And the bottom line there, where it says allow password type, basically what's happening there is you're declaring this is where the password file goes, and you're allowing this etc. type to actually relabel it, which is to change the label of it, a very powerful permission. And so, that looks sort of like a benign line, but that actually is a very powerful thing, and that could actually cause you to compromise the system unless it's configured correctly. Who can now do this becomes very important. And so I just want to show you some of the complexity of it. Even though it looks simple, there's a lot of things in here that have to be analyzed. So how do you know you have it right? That language I just showed you is really the equivalent of like C language. C without lint. So it's just like one notch above assembly language. So you don't have things like scoping, right? So if I have a file over here and I'm talking about the password file and I say, I only going to have this guy and this guy, they're going to be able to access it. Nobody else can access it. That's my policy. That's great. And you look at that file, that's great. Well, over here, somebody can say, I need access to the password file. I'm just going to give my guy access to it. So, in this file, it looks like everything's fine. You have to look at all the files that are combined in one big file to understand it. Now, at Tresys, we've created a tool called APOL that helps you it basically combines all those files and lets you run queries on the whole policy as a whole. I'll talk more about that in the end, but that's your only hope at this point, because without any scoping, anybody can touch any other file and you've got a problem. It's basically just like C. And so you've got all the problems of C, and you don't have any of the type checking of C. So or of like a lint program. So more work is needed there. So if you think about it, the bottom line, one thing I'd like you to take away from this, if nothing else, is that creating security policies is hard. When we first started doing, security, 17 years ago when I started on it, we were thinking, oh, analyzing the system. We're going to analyze the operating system, make sure the operating system is secure. We're going to build all these layers. That's the hard problem. When we're all done, we'll just make the security policy, and it'll keep everything separate, and that'll be great. And as we go forward now, we're realizing that security policy is a significant piece of engineering that's hard. It almost approaches the complexity of software engineering. Because if you think about it, if you're going to do a true least privilege policy for each program on your system that's important, you have to know what resources does that program need, how does that program talk to other programs, how they interface. Maybe the program is grabbing a bunch of this greedy program bullet here at the end. Maybe the program is grabbing a bunch of resources. It's touching a lot of things. You'd be amazed at how many programs have the ability want to write stuff into temp that you never realized they did. And so you have to say, well, gee, it doesn't need to do that. I want to take that permission away because it's going to violate my security policy. So developing security policies is hard. There's a whole science of engineering there that becomes also merged with your software development process to not only develop the security policy, but basically change the software development process, making things smaller and more modular so you can analyze them. And it's a whole engineering that sort of some of the people at Secure Computing, that I and the people at Tresys have sort of a gut feeling for, but we have to sort of build that into a science. One of the things with all this analysis you're trying to do is trying to avoid trusted processes. Because like, for example, when I talked about that labeler example, right? A very small program that you actually have a hope of analyzing. Well, for every program on your system you have to analyze, that causes you more work. Now that labeler example I used is very small. You'll find as you start doing a real system, especially if you're going into an existing system where there's already a lot of components and system components, there's a lot of existing software and it's thousands of lines long. Now how are you going to analyze that to make sure that that's doing only what it's supposed to do? I mean, you'd have to specify the program and then analyze all the code. It's very expensive. It's doable. I have a question personally if it's economically doable. And of course, that's what in a lot of the work going on here and around the country is trying to do, find economical ways of analyzing software to make sure that it meets certain requirements. So the whole goal then is when the security analysis as I'm performing here is I want to minimize the number of trusted process. Because for every trusted process I find I'll wind up in my final system, then the cost of analyzing goes up. And as from a reality point of view, I also know that if the number of trusted processes gets too high, people start doing triage and saying, that's a trusted process, but I think it's okay. And you'll just kind of sweep it under the rug and nobody does analyze it, which, is hiding the security problem. But so it's very important then when you identify a trusted program, you have to know what it's trusted to do. Like that labeler program, the important thing there is that it labels the file correctly. And you'll think about it, I make sure it doesn't want to modify the data. That would be bad. Or that it doesn't keep state. So when the next file comes through, and maybe it's labeled correctly. So there's all kinds of things you'll have to analyze, but it'll be a small list, but you have to have that list to know what the program's going to do. The other thing that for each trusted program, and this is a problem I see in a lot of the systems I'm getting that other people have analyzed, is people won't control the executable for the trusted program. If you think about it, the trusted program is a program that you've analyzed. You spent a great deal of effort proving that this program only does what it's supposed to do. And you've compiled it, and it's great. There it is. Well, now that you've got that executable, you have to guard that executable like a hawk because, of course, that's what an attacker is going to try to do is change the executable to get the behavior they want out of it. And, for example, does this program, if you linked your program using a shared library, okay, so maybe I'm controlling who can write the executable. That's great. I'm covered. Oh, but I used a shared library. Now somebody can change the shared library on me, and they change the behavior of the program. So you have this sort of transitive closure thing that you have to analyze. All right, so in preparation for this talk, I sort of made, as I started trying to vaguely coalesce these sort of tricks that I have in my mind into a process, I came up with a vaguish waterfall model here. And so you start with your security goals, which are what are the properties about the system that you want to prove. And so you start with your goals, and from there you can do your analysis. And then once you've got your analysis complete and everything looks good, let's go try it out in the real system and see what happens. So the output of the goals section is a bunch of concrete goals that you can actually check. And I'll talk more about them, but they're going to be fairly simple, things you understand pretty clearly. Then in the analysis, you'll make sure that you'll be analyzing the program and the system as a whole to make sure that everything that you have as a goal, yeah, the system is doing that. It's meeting those goals. And then once you're done with the analysis, then you move on to the testing, and you make sure that everything works as you expected. Because in reality, oftentimes there's functional things that don't really work out. For example, a lot of programs, maybe it'll touch some resource. Like maybe some program you didn't realize all of a sudden has to read and write to the etc. directory, maybe change the password file for some obscure case. And you're stuck with it. You can't get rid of it for some reason. Well, now it's violating your process. And so it's violating your goals. And so now you're going to have to note that and either trust the program or something. So you have to note that and move on. And so what happens is you never change your security goals, but you'll find exceptions to your goals. In a real system, it's not going to be some sort of clean, mathematically precise system. You'll find, okay, here's a process, and it's doing, it's moving data, and it's violating my goal. I'm stuck with it. Now, you can't just ignore it. You have to annotate it, and it becomes a trusted program if you can, and that's part of the analysis. So what are the security goals? Basically, they're going to be high-level things, things that are really easy to understand, and they'll basically probably be the person who's giving you the requirements will lay out the high-level goals for you, and then you'll kind of refine them and make sure that they're consistent and stuff. So they should be easy to understand, and they could be something you can test. I got some examples here on the next slide. For example, for a firewall, right? Very important piece of security software. You'll have, and this is how the Sidewinder firewall works, right? Stuff comes in from a network interface card, and it goes through a series of filters. The job of each filter is to make sure that it passes the certain checks, and then it goes out the other network side, other network card on the other side to maybe the inside of the network after it says everything's okay. So the important policy then is that that no packet can get through the system without going through each one of the filters, which I've then analyzed to make sure they're doing their job. So that's what a firewall policy would look like. Maybe another example of that would be you have a firewall, but you don't want to have the administrator interface from the outside, maybe the internet exposed high-risk network. I mean, you could, but say your policy is to not have the administrator have that interface. So that's a high-level goal, and you want to write that down and you want to analyze it to make sure that that property holds. Another system is like, say you have a multi-user system where you have data and you just want to keep things separate. I've only got space for one CPU, and I've only got 2 users, and I want to keep them separate. That's another thing. It sort of gets to that 2 buckets problem. So you want to keep the data separate between the 2 things, which may sound simple, but can be quite complicated. So when you start doing the analysis, the first thing you're going to do is you're basically going to be looking through the analysis, and you're going to be trying to find the trusted programs. Because again, the trusted programs are the ones that are going to give you the most problems. They're the ones that are going to raise the cost factor of your analysis, and so you want to minimize those. That pretty much sums up security analysis. I mean, there's a lot of architectural things you do trying to make components small so that you can do a true least privilege policy on them. But really, all it really gets down to is minimizing the number of trusted programs. Because if you have small modules, then you've got much more analyzable code. So let's talk about the types of trusted programs. And the first class is the one that you expect, right? This is the program like the labeler program. It's trusted because it needs to be trusted to do its job. It's a labeler. It has to label the data correctly. So it's trusted. I'll analyze it, make sure it does its job. So that's your one class. That's the class that everybody thinks of. But the other ones, of course, are your critical infrastructure. in the later stages of this high assurance system that we were building for the government, we made a file system. And so the file system was a separate daemon that ran on top of those. We built an operating system right from the metal up several layers, and so everything was memory and objects. There were no files. But then we built a file system on top of it as a separate system, and we used the underlying type enforcement to constrain the file system so that it couldn't go randomly write willy-nilly into the MMU, or it couldn't change the storage manager and other things. So basically, as another class of trusted program, they're providing critical infrastructure. The system developers are building those, and the operating system basically falls into that piece as well. But the bottom one here is the worst kind of trusted program, because basically you do the analysis and you realize, oh, this program's trusted because it's going to violate my security goals, but that's the only reason it's trusted, is because it has to be trusted because it's going to violate my security goals. And you'll find that over and over again. You'll find sendmail is going to, or like FTP will all of a sudden have to touch this other directory, and it's like, well, no, that will violate my whole separation problem here. It's like, well, no, it needs to do that or it won't work. And so are you going to abandon FTP? Well, if you want a standard interface, no, you can't. So you're stuck with it. And so you then have to go to these other mechanisms I talked about. So for example, sendmail, and I was chatting with Jacques? Yes, Jacques earlier about sendmail, and there's QMail now, where they've taken sendmail and they've split it up into a bunch of smaller components. So that's a significant piece of engineering, to take this large sendmail program that everyone was sort of stuck with and break it into smaller components. But now when you have the smaller components, you can treat each resource separately and protect it with type enforcement, and you can get a much more trustworthy system in the end. And hopefully it works a lot better than sendmail. The other pattern that's often used is that wrapper pattern I talked about, where you'll take the large program like sendmail, and you'll just put another smaller trusted program that will check the critical property that you're interested in. I'm never going to analyze sendmail, but the one thing I'm really interested in, I can do this. Maybe I didn't get everything I wanted, but I can check this one property to make sure that that's okay. Like maybe there's no attachments on the mail message. So you write a small program that checks that. That sits outside of sendmail, and you've got maybe your critical thing done for your mission. All right, now in that previous slide when I was talking about type enforcement, I showed you this really nice sort of like cell-like architecture, and that sort of gets you into thinking about what type enforcement is, where you have a domain, there's a program that sits in that domain, and it has a bunch of resources, and maybe even other programs that run in that domain, but it's a happy little community, and then these tight little interfaces that you talk back and forth to other domains. That's true, but in a real system, it's really like a really messy Venn diagram where all the domains are talking to all kinds of other domains. The amount of the data, as you start looking at an operating system, and if you take each program that's critical and you put it in its own domain, and you see how much information has to flow just to get the system to work, you'd be amazed at the number of links that are to move data back and forth. So what it really boils down to is a graph problem, where you have each domain represents a node on the graph, and how the domains interact with other domains is the arc between, and then the arcs come in different flavors. Maybe you can write a file, and so that's sort of like a high bandwidth communication channel where one can move a lot of data. Maybe it's just as simple as I can write files into a directory, and now somebody else can see that file exists. Now that doesn't convey a lot of information, but it conveys some information, and so that becomes another choice. So they're not all equal. All the arcs aren't equal, so there's weighted arcs here. So the whole idea then of this information flow analysis, suppose my question is I have domains A and domain B, and I want to make sure that no data moves from domain A to domain B. So you start doing analysis, and what we do at Tresys is we have this tool called APOL. It's open source. It's available on our website. It loads in the SE Linux policy, and you can put a goal in it. I have domain A, and I have domain B. Let me know, do an information flow analysis to tell me how many paths there are between A and B. And since they all it's an operating system, right? And they all have shared resources. They all depend on the operating system, or they'll depend on any number of other factors. You'll get flows. And now you have to look at all those flows and determine, is this an operating system component that's trusted, or because it has to be trusted? Or is this a small program that I can eliminate? And so it sort of becomes this game of looking at all the nodes and finding out which node can I eliminate or rearrange the graph so I can get rid of it. You'll look at things like, is each link necessary? Does this program really need to access that resource? A lot of, when you look at SE Linux, and this is the philosophy that Red Hat is using, it's a great idea because to get people to use type enforcement, the system has to work. So they're starting out with a policy that's not a least privilege policy, but it's a policy that works. It has much larger granularity, but it gets people started using SE Linux, and then they can basically shrink wrap it with, put a hot blowgun on it and like sort of shrink wrap it, the security policy down to its least privilege policy. That's their plan. But if you go into an existing system, the number of links it's sort of overwhelming. And so you have to look at, you'll have a program like sendmail touching things like the web server. Why is it doing that? Or it has the ability to write, configuration files for maybe the X server. And it doesn't make any sense, but that's in the policy. And so you have to say, well, I can take that out. And so then you have to, that's the kind of analysis you're doing. And so then basically you're basically trying to eliminate these links. Another approach is you say, well, this is a link, but it's not a high value link. Maybe all they can do is they can see files that appear in this directory. The files only appear in the directory when something else happens that's beyond the user control. I'll live with that. I mean, because again, it gets down to these economic issues. Maybe I can fix it, but I'm going to have to write a new software package. I'm going to have to take like sendmail and bust it up like into Qmail. That's a lot of work, and so maybe I can't do that for this run. So you find other things. Other things is you might find like, well, in this flow, maybe A, D, and I, they're untrusted programs, large programs, sendmail. But C is a small program, and it's already trusted. I had to trust it for something else, so that's okay then. So this flow that exists between A and B is okay because C is a trusted program, and it's not going to violate your goal. And other things you can do is you can re-architect the system. You could use those sub-roles I talked about, subdomains, to shift things around so they don't apply, so that the flows don't happen. So in the end, then it becomes the information flow analysis becomes looking at the graph. Now in the APOL tool, you don't actually get a graph. You get a list of domains, basically with little arrows hooking all the domains in a chain, and each arrow is basically telling you what the axis is. This domain can read-write this file that this domain can then read, and then so you have to follow this chain of reasoning. So it becomes a complex analysis task, and we're trying to improve it, but it basically gets down to you have a very nasty graph and you have to look at it. And you have to check and basically use these tricks that I've talked about to get rid of it. So now this is just a list of things that you have to look at that maybe wasn't totally obvious to you. As I talked about in the beginning, you set up your security goals, and those are basically like your software design goals that you're trying to satisfy. So you have to obviously check those goals. And one of the things that will fall out of that, well, here are the programs that are trusted. Here's a labeler program. Here's the file system. I got to trust that. Maybe I'm stuck with sendmail. I got to trust that. So that's in here. And then you have to then say, okay, well, if it's a trusted program, then I have to make sure I know what that executable is, and that maybe I can't even analyze it. Maybe for economic reasons, I can't analyze the program. I still want to make sure that nobody else can modify that executable or change its shared libraries that it uses or anything like that. So you have to do that. Another problem you'll see is that this is a trusted program. It can execute shell scripts, so it can then run interpreted code. It's another bad thing. You don't want trusted programs being able to run interpreted code. You only want them to run well-defined code. So there's another thing I sort of glossed over about SE Linux, and that's because SE Linux sits on top of regular Linux. So what happens is you can turn a regular Linux system into an SE Linux system, but you have to all of a sudden label all these files. And so there's this file called the context file, which basically has a path name. It says for anything in this path name, give it this type of data. And it's done on boot up, and you can configure it so it does it every boot up, or once you get to a secure state, you don't have to do this every time. But that's very important. That becomes part of your analysis, because if I've done all this analysis in the type enforcement policy, I have to make sure it actually maps the actual files in the system correctly. And so you got to get your file context file correct. There's another one I only glossed on, a very powerful permission that's in SE Linux, which is the relabel permission. It allows you to relabel a type, change it from one type to another type. Now, you think, well, maybe that's too powerful. We shouldn't have that. Well, in reality, you'll have things like the system when you're logging in, right? That's owned by the login prompt is owned by the system. But once you type in and log in your password, it's authenticated for you now. Now it should be running in your name. So now you have to transition the type into your user type. So it's something that's very much needed, but it's a very powerful thing. So that has to be analyzed, making sure that nobody can change any types that would surprise anyone. And of course, then again, who can change the policy? The best systems I like are the ones where it's static from boot up, and nobody can change the policy where the system is running. You take the system down in sort of administrative mode where you've cut off network access, and then you can change the policy, and then you bring it back up in normal mode. Not all systems can handle that, and maybe that's a bit paranoid, but that's who I am. You be in security for a while, you become really paranoid. You know, you get an email, you look twice. Does that person really love me? I don't think so. Okay, so that covers basically the security goals section. Then you've got the analysis section. The third phase was this testing section. And security testing is just like software testing. As I've said, the security policy is almost as complex as software. Once the system is done, say I've tightened down, I thought, oh, sendmail doesn't need all this access. I've gotten rid of a bunch of access for sendmail. This is good. Now the sendmail will be much more secure. You have to go run the system. Sendmail may not run anymore because it actually needs those resources that you thought it didn't need. And that's a surprising thing you'll find over and over again. Not on sendmail, but on the web server, you know, or there'll be some bizarre feature that's rarely used. But once it's used and that user can't use it anymore, they're going to come looking to you to fix the problem. So you have to do a bunch of security testing. Ideally, you'd like to do total regression testing, where you execute each line of code, because then you would know that each resource that the program would have accessed has been accessed, and you know it has access, and it's got the right access, and that kind of stuff. Obviously, very expensive, and not something you want to be able to do. I'm going to step it up here. DARPA has a very interesting program that's like the SETI program, where they're looking for signals from space, where basically they're going to divide up the problem, where people analyze and watch a program to see what resources it needs, and then people are going to compare lists. They can build up a complete list of what resources a program needs. So basically, security testing is going to cover architectural flaws, things you didn't realize. You're going to cry when you find them because you're going to have to go back and do a bunch more analysis. But you also find coding flaws, and you can move forward fixing those coding flaws. It's just a necessary evil, just like software testing. So the big thing is, unlike software, where you have to do a whole bunch of coding, which is much more time intensive, if you can fix the problem with security policy, it's much more economical. You can get it done a lot faster, because you can make maybe one line change in the policy file, and now that program is constrained and it can't take maybe there's a code exploit where somebody can write a config file, and they're doing a buffer overflow, then they're being able to write a config file. Well, if you take the ability for the program to write the config file away, even though the buffer overflow stack is there and you haven't fixed it, they still can't write that config file, and you've shut down the avenue much more economically. If there's a flaw in the security policy, it doesn't necessarily mean there's a flaw in the system. You know, it's basically like a layered defense, right? So the security program that's running is one layer, and then the policy is another layer. And so it often takes a conjunction of two flaws to actually get through the system. But the whole point of security policy is there as that guide rail. In case your program fails, you're going to limit the amount of damage that the program can do. If an attacker, say, gets into sendmail and takes control of it, you're going to limit the kind of access they have. So just to wrap it up here, there's a lot of economic factors driving this analysis. When I first started, it was going to be all ivory tower stuff. We're going to do everything right down to the metal. We're going to assure things. There will be no unemployed mathematicians in Minneapolis because they're going to be all proving this code. Well, in the end, it turns out we couldn't afford all the mathematicians, and they're now writing software for other companies. But economics becomes a huge factor in computer security, and I just can't stress that enough, because even when you're doing an analysis within certain time constraints, you just can't analyze everything. You have to pick the most effective things to analyze and look at those first. stop the overt channels before you start looking for the covert channels. Covert channels are still important, but if you don't close the overt channels, you're not really getting the most bang for your buck. So you basically have to pick the most effective analysis. Basically, the security policy is there as an economics tool. It is sometimes much more economical to change your security policy than to change your software. Even though the right thing to do is to change the software, maybe you can't afford it, but you can change the policy and you can get at least some sort of fix out of the deal. And basically, the bottom line here is just because security policy is hard, there's no reason to ignore it. It really is a significant engineering effort that needs to be analyzed, and hopefully we can build up a better science of policy engineering with courses and everything. So that's my talk. I think we have time for a few questions. We do have another lecture coming in here afterwards. But... Yes.
In SC Linux, our policies just allow, positive things?
Nope, you have denies as well.
Okay.
And you can also have constraints. So I can specify, say in that policy file I was talking about, I can say nobody else should have access to this file except these things that I've listed here. So if you specify all these constraints, you can kind of cover yourself, but it's not as good as scoping because you have to seriously think and put all the exceptions in. And so it becomes set operations. It's possible. And so it's a very flexible, powerful language. And I hope I didn't give you the impression that it's flawed. It's just where we are today. We have to just start adding more abstractions to it now that we learned to work with this, put in scoping rules and stuff. Yes?
I think you touched on this earlier when you were talking about your concerns about the relabeling operation in particular. Let's imagine for a moment that sendmail has buffer overflow vulnerability and it's exploited. Does the system still recognize that as sendmail, or could it possibly recognize it as something else?
No, the system would still recognize it as sendmail. The whole point of type enforcement is to prevent sendmail from then launching into other attacks. When I was at Secure Computing, we actually had a challenge for our firewall. We let you log into the firewall, and we gave you a whole suite of tools. And they say, you're in a domain, see if you can get out. And so basically, that's the point. So you could do, it still thought you were sendmail, even though you're running a shell. But then we restricted your access.
That was my concern, because there is a strong reliance on the fact that once something is exploited, it's still going to be recognized as the same thing.
Right.
By the system.
And in reality, right, there still are holes out of sendmail to the rest of the system. And now, if you have a shell command, can you get through those holes? That becomes the next question. But you've raised the bar. You made it a lot harder. More questions? Yes?
Yes. I heard you mention sendmail a lot of times.
Yes, it's fun to pick on sendmail.
And I would like to know if there are other programs. The whole point is minimizing the trusted programs. Those are the programs that kind of throw the wrench in the works.
Well, they raise the cost. If it was cheap to do trusted programs, it'd be great. You could trust everything. That would be a fine solution. But the problem is economically, that's just too expensive.
I would like to know if there are these lists of programs that you come across, like sendmail, for example, that access a lot of resources that you don't know why they're accessing, that would have, if you just remove the program from the graph or the system, everything would be beautiful. Have you come across in your experience?
In the specific analysis I've done, I found specific things. Of course, I'm analyzing things for very specific applications. I want to do more general analysis of the system, but I haven't had time. But that'd be a great research project. So. Yes. Behind you. Sorry.
How do you handle patch management and upgrades? Does that mean
you can build that into your policy, right? You could have a patch manager cell where it has the ability to change the executable, but you put a filter in front of it so that maybe it can only be loaded, through the system administrator, and then it has the ability to change this executable or patch it or run whatever stuff. Now, a program like RPM, that'd be a little bit more tricky because RPM has a lot of permissions because it touches a lot of different things. And RPM, I think, is another good example of the program that touches a lot more stuff than what you'd want it to touch. But if you can envision a very specific program that could do some very specific patch management. How are we doing on time? Yeah. We got to go? We got to go. All right. I can hang out in the hall if you want to have more questions. Thank you.